Hi, my name is Dhiren Pratap Rai, a geophysicist of Ray Speed Solutions Private Limited. Today, I am here to talk how existing seismic can be improved with our advanced seismic processing technique and can increase the reliability of interpretation. The title of the talk is Improving Seismic Imaging of a Complex Fault Thrust Belt in Mindoro, Philippines. So, the brief outline of talk of the 2D land seismic data. Further, we will discuss what was the objective behind reprocessing work, acquisition parameters. We'll review data quality and some process stack sections. We'll see the comparison between original processing versus reprocessing PSTM stack. Then we'll discuss the spectral extrapolation techniques and their results. Then the summary of work. Objective of work. So the motivation of this kind of work is to enhancement of existing seismic in order to bring out geological structure and increase resolution for the better imaging. Acquisition parameters. So here we can see the data was recorded in 2010 with nominal CDP fold 90, sample rate 2 millisecond, recording length 6000 millisecond. Let's see couple of process data examples. The main target of reprocessing was to improve the overall PSTM section and bring significant information at approximately 200 to 1200 millisecond two-way time below surface. Our production processing sequence that used provided a consistent and comprehensive solution while simultaneously maintaining the true amplitude during all the stages of processing sequence. Our pre-stack time migration also improved the imaging of the final stack data, result in significant improvement overall the original processing. Well, here we see the quality of recorded data. Left side we have couple of sort gathers and right side stack without any application. So from here we can see linear noise associated with direct arrival. Also there was ambient noise, random noise with the ground load being very high in area close to the main boundary fault. So here we can see the result after noise attenuation. Our noise attenuation process have been successful while still preserving native amplitude information, resulting in improvement in seismic. In addition, good protection of the entire primary signal and event continuity with standby. Here we have left side deconvolution stack and right side after two passes of residual stack. Till this stage, there were several processes applied to improve the signal to noise ratio and improve the stack response of the seismic. Extensive testing was done at every stage of the processing to achieve optimum parameters. Also, our past experience with these data fields has shown that static correction and velocity are an important factor in optimizing continuity, resolution, and overall structural imaging. Therefore, we paid special attention to these areas. Well, on residual statics corrected CDP gathers, a CDP domain noise attenuation was applied to clean the data as much as possible before migration. The left side stack representing after CDP domain noise attenuation, and it provides a better stack section with balanced amplitude. Prior to PSTM, offset regularization and 2D interpolation was ran. The stack response is plotted at right side. Now let's see the comparison between original PSTM and reprocessed PSTM. In this slide, we have existing seismic PSTM. Yellow boxes representing key areas that need improvement in reprocessing work. On the right side is a zoomed in section and represents the basement structure, which also needs to be improved. The reprocessed PSTM image shows significant improvement and impressive uplift over the original processing result and provides a very detailed information and is bringing a good structural information as a whole. Also, the structure high is better defined in the reprocessed data image with improved layer continuity, thus leading to a greater confidence to the final interpretation product. Then we applied the spectral extrapolation method to a legacy onshore 2D seismic data. This technique is our partner's proprietary. Spectral extrapolation. It is a bandwidth extension technique that can be implemented by combining spectral inversion with constant time variant wavelet extraction and targeted bandpass filtering. By performing a spectral extrapolation, we may broaden the band of the data and able to increase resolution and see more details. So this really helps where we have the thin layers. As shown in figure 1, the difference before and after application of spectral extrapolation on conventional seismic. The authentication of application was verified with well-logged data. Also, this technique helps in detection and characterization of thin reservoirs that are not mappable with conventional seismic frequencies. So, as shown in figure 2, is an example of a large channel as we can see on a conventional seismic, but we know the difficulties where this type of layer and distinguish this kind of layer. However, by performing a spectral extrapolation application to the conventional seismic, a large channel is easily mappable. Well, here we discuss how a spectral extrapolation works. So basically, it uses seismic band to predict frequencies outside the seismic band. For this, we need to find a relationship at the lower frequencies. This relationship is used to predict the frequencies outside the seismic band. In this case, for the 2D land data, 5 to 50 Hz was used to predict the frequencies outside the seismic band. After the application, it extends the frequency domain response far outside the wavelet band. Here we have conventional PSTM seismic results with and without interpretation. Also, right side we can see frequency spectrum and statistical wavelet extracted for the input data. In this slide, we will see a spectral extrapolation result over conventional seismic. So here we can clearly see AC technique produced a high vertical resolution that is double that of the original seismic data based on frequency bandwidth. So figure 1 representing frequency spectra, orange color represents conventional seismic and green color represents spectral extrapolation. Thin layer observed in AC result also correspond to those in the sonic and density logs. Apart from higher resolution, a spectrally extrapolated image enables better interpretation of geological features. And of course, with good well ties and the application of AC, it is possible to map petroleum elements with greater confidence for minimum outlay cost. Significant risk reduction of future appraisal and development wells can be achieved. Figure 2 showing the statistical wavelet extracted for the AC data, and the AC data wavelet has significantly improved time compactness corresponding to a higher resolution seismic image. Summary. Now the summary of work. The reprocessing shows significant improvement and impressive uplift over the original processing. Also, It provides very detailed information and is bringing a good structural information as a whole. After spectral extrapolation application, thin layers are observed and it enhances stratigraphic and geomorphological details throughout the section. As a result, interpretation of geological features and additional horizon within the interval of interest can be done. Thank you for your time and thank you to the collaborators.